Hello, everyone. Thank you for coming to my talk. I'm Omar Wasim. I'm a first-year PhD student at Northeastern University, and this is joint work with my master's supervisor, Valerie King, at the University of Victoria. And today I'm going to be talking about fully dynamic algorithms for max-cut. So the max-cut problem in the undirected, unweighted setting uh, asks to find a cut C, which is a partition of vertices, such that the number of crossing edges between the partition is maximized. So in this case, we can see that these green edges are the we'll refer to these as cut edges, and the pink edges are the non-cut edges. And here the cut is simply the partition which is given by the vertices on the left-hand side and the right-hand side, such that the union is the whole set of vertices of the graph. So max cut is a canonical NP-hard problem. In fact, it's even hard to approximate better than 0.878 under the Ames conjecture. Moreover, a t-approximation algorithm for the max cut problem, since it's NP-hard, so what we can hope for in polynomial time is an approximation algorithm, which gets a solution which is nearly optimal. In fact, this t-approximation algorithm is going to return a cut such that the number of edges contained in the cut is at least t times the optimal solution. So we would like to make a distinction here between respecting cuts versus approximate cuts, because in this paper, in this talk, we will be referring to algorithms which get respecting cuts. So respecting cuts are somewhat of a stronger notion as compared to approximate cuts. So we say that a cut C is t-respecting if the number of edges in that cut is at least a t fraction of the total number of edges for some constant t in between 0 and 1. And so it's easy to see that a t-respecting cut is always a t-approximate cut, but not vice versa. And this reason for this is that the number of edges E uh, is actually an upper bound on the maximum number of edges contained in any cut. So for the example of K2n, the complete graph on 2n vertices, here a maximum cut, it's easy to verify that the maximum cut is any cut which has n vertices on each side. And so for large n, we see that a half respecting cut can be of the size, can have the number of edges which is roughly twice as large as a half approximate cut. So, so sometimes a t-respecting cut can be much bigger in the sense that it can have a lot of cut edges as compared to a t approximate cut. So now we'd like to just talk about some known results in the static setting where the graph is not changing. So we're just given a graph, we want to return a cut. So Johnson's half approximation algorithm is probably the most well-known algorithm. It yields a half respecting cut. The state of the art, however, is a 0.878 approximation. Is due to Gomans and Williamson and their solve an SDB program to attain this approximation. Aurora-Kale's primal dual algorithm gets nearly a 0.878 approximation, but the running time is sort of dependent on the quality of the approximation. But we can assume that for constant epsilon, it runs in linear time. On the other hand, there's a spectral algorithm due to Trevisan, which gives a 0.62 approximation. And there's a nice combinatorial algorithm, which is an analog of the spectral algorithm due to Kale and Seshadri. So what we observe from here is that Johnson's greedy max cut is in fact the only algorithm that we know which gives a half respecting cut in linear time. So the Johnson's greedy max cut algorithm, it's a greedy algorithm. So it just starts with initially only just one vertex on this one side of the cut, and for every successive vertex, we place it on the side of the cut, which maximizes the number of cut edges with respect to the current cut in every iteration that we have. So this is easy to see. It's a linear time algorithm, and at least half the edges examined in iteration is included in the cut, and so this gives a half respecting cut. So the talk is actually about fully dynamic algorithms. So let's just define those algorithms. So fully dynamic algorithms are algorithms which handle changes the underlying graph. And those changes, we assume that there will be edge updates instead of vertex updates. So the vertex set of the graph is fixed, and there will be edge insertions or deletions um, with respect to time. And the goal of a dynamic algorithm in general is to maintain a property faster than the best static algorithm. So we just don't want to brute force and run the static algorithm from scratch each time. And so this is where actually dynamic algorithms come into play. Most commonly, however, the problems which are polynomially time solvable have been studied in this literature. Only recently, following the seminal work of Onek and Rubenfeld, have people actually started studying dynamic versions of NP-hard or NP-complete problems. So this is sort of initiated work in dynamic approximation algorithms. Some of the most recent results include algorithms for set cover, coloring, independent set, and so on and so forth. So in the dynamic max cut problem, well, we have an empty graph initially, and there are edge updates going on. We would like to maintain a half respecting cut. So the half respect, so this quality is half respecting cuts. We would like to just we'll just try to get an algorithm. We'll just try to get algorithms which give us or which maintain a half respecting cut after each edge update in the graph. And so as you can see in these graphs, the cuts are actually changing, and so we would like to maintain a cut after each update. And we would also like to answer queries in constant time, such as whether an edge is contained in the cut or not, and the total number of edges contained in the cut, and the size of the vertex partitions of the cut. So first step is to just probably use a known static algorithm and make it fully dynamic by using periodic rebuilding of the data structure over epsilon m updates. And so this actually gives us a slight loss in the approximation, but it doesn't quite give us a very efficient algorithm to maintain a half respecting cut. So if we invoke this observation, which tells us that we can get a t minus epsilon respecting cut in t over epsilon m worst case update time, where mn is just simply the running time of a known static algorithm, then if we invoke this observation, then we can see that to maintain a half minus epsilon respecting cut, well, we can just use Johnson's greedy max cut algorithm, wait for epsilon m updates, and during those epsilon m updates, you're going to rebuild the data structure, and we're only going to suffer a loss of epsilon in the respecting ratio. So if we, again, the same idea can actually yield a polylogarithmic worst case update time algorithm for a fixed constant epsilon greater than 0 to maintain a 0.878 minus epsilon approximation. And this is due to Aurora by using Aurora and Kale's static algorithm. We also note that if we use Aurora and Kale's algorithm and we use Charikar and Wirth's rounding technique, we can also get a half respecting cut. But like when the optimal solution, when the optimal cut is actually sort of dense, this is not going to give us a great or a sublinear in n update time. So the goal of this work in this talk, we'll be talking about algorithms which guarantee a half respecting cut after any edge update in sublinear update time. So our first result is an O delta worst case update time algorithm, where delta actually denotes the maximum degree. Secondly, we show how to generalize this algorithm in the fully dynamic MPC setting. This gives us a very nice distributed algorithm is almost constant round and adjustment complexity. So here the adjustment complexity just simply refers to the number of changes that we're making to the underlying cut. And then we improve the running time of um, in the sequential setting, and we get like two fully dynamic algorithms which have sublinear in M and sublinear in N uh, update times respectively. So to obtain a delta update time, what we see is that there are two main updates that we're actually concerned about, so which would actually lead the cut to degrade. The first is insertion of a non-cut edge, which might lead to a corresponding decrease in the size of the cut we're maintaining, and the deletion of a cut edge. So main observation is that whenever a cut ceases to be half respecting, we can always find a vertex which, if we move from one side of the cut to the other side, we can always increase the number of cut edges. Right. So in this diagram, we can see that these red vertices are switching vertices. Let me just, yeah. So if we have that a cut is not half respecting, then there must always exist a switching vertex. And the reason for that, the simple reason is that if not, then every vertex must be incident to at least half its neighbors. And so that would actually give us a half respecting cut. So if a cut is not half respecting, then we must have a switching vertex. So the delta update time algorithm simply just maintains a set of switching vertices. Each time a cut actually degrades below half respecting, well, we just switch a vertex, and the switched vertex in turn updates all its neighbors, which might become switching or non-switching, and the switched vertex using so the time taken for the switched vertex to update all its neighbors is simply O of delta. And we would like to make a remark here that the switching vertices are not necessarily the endpoints of the updated edge. The counter example is fairly straightforward. However, we would like to remark here that for problems such as maximum matching and vertex cover, sometimes in those type of problems, we can get very fast algorithms because of the fact that we only need to look at the endpoints of the updated, or a neighborhood of the endpoints of the updated edge. However, this might not be true in the max cut problem. So yeah. So just quickly going through the MPC model in a static setting where we have a synchronous all-to-all communication network. We want sublinear machine per sublinear number of machines and sublinear memory per machine. And this capital N actually denotes the size of the graph problem, which is the number of edges and the number of vertices. In a single round, well, a machine simply receives messages of the previous round from other machines. It does local polynomially bounded computation, and then it sends messages to all other machines. So this is the static setting of the MPC, and typically we would like to get algorithms which have at most polylogarithmic round complexity. So dynamic algorithms in the MPC setting have been recently studied by Italiano, Durfee, Novicki, and Onak. And so the goal of dynamic algorithms in the MPC model is quite similar to that in the sequential setting. Well, because we just want algorithms which can efficiently handle updates while taking fewer number of rounds, messages, total number of machines involved in the communication, and if we can minimize the total number of machines that we use in our algorithm, that would also be nice. So based on our delta update time algorithm, we get an efficient distributed algorithm in the MPC setting. So it's a very simple implementation. So we just choose a coordinator machine with the highest ID, which is going to store all the switching vertices, and for any edge update, only the machines corresponding to those vertices are informed, and the coordinator then picks an arbitrary switching vertex, and so on and so forth. So this actually takes O of delta messages and O of 1 rounds. It's a very simple adaptation to the MPC model. So that's pretty nice. For more details and due to time constraints, I might not be able to go into detail of this algorithm. It's very straightforward. Now back to the sequential setting. If you want sublinear update time, we already have a delta update time algorithm, and for this algorithm, well, the update time for large delta can be as much as O of n, so that's not great. So to reduce this running time, well, uh, we get a square root of m update algorithm, and the main techniques that we use to get that algorithm is a partitioning technique of G into vertex disjoint induced subgraphs, and then we combine the cuts which are maintained on those subgraphs. So the idea is that we would just use the delta update algorithm on vertex disjoint induced subgraphs, and to combine, however, the cuts, any two half-respecting cuts, we'll need to consider the edge counts, which are the number of edges between these pieces, between these individual subsets of vertices. And in this case, if there are only two cuts we're maintaining, then there will be four such edge counts. And the claim is that if we merge these two cuts, then there must be a combination which is half respecting. So all what we need to do now is find an efficient partition which allows us to reduce the update time. So you partition V into high and low degree vertices. Low degree vertex is simply a vertex with degree which is less than square root of m. Otherwise, it's a high degree vertex. We separately maintain half respecting cuts on a set of low and high degree vertices respectively. Our algorithm actually consists of phases. Each phase has only square root of m updates, and for the specific value of m, k, um, well, we would like a high and low degree vertex partition, and we want to recompute, we want to reinitialize all the data structures after square root of mk updates. So the amortized update time for the recomputation is just O of square root mk, which is good. So the main technique actually involves ideas involving lazy updates of low degree vertices. So, uh, so if we have a low degree vertex, then its degree is obviously less than square root of m by definition. And the main technique that we use that if the vertex is high degree, we update all its neighbors. On the other hand, if we have a low degree vertex, we can afford to actually update all its neighbors. But if a high degree vertex switches in its cut, then we'll only update its high degree neighbors. So we'll only let the high degree neighbors know of that vertex's switch. However, this wouldn't actually allow edge counts to be maintained anymore accurately. So how can we deal with such partial information? Well, we sort of maintain this invariant at all times, that if V is a high degree vertex, then all data structures are up to date. And so the easy case is really when an edge update is between a high and a low degree vertex. In that case, only those edge counts need to be maintained between these four blue pieces, and this only takes constant time. However, um, if both the endpoints of the updated edge are high degree vertices, we use the delta update time algorithm to update C2. And what we'll do, so this is pretty simple. If the edge update actually involves high degree vertices. On the other hand, if the vertices are low degree, then we again use the delta update time algorithm to maintain a half respecting cut on this partition V low, and we only, however, update. So we can actually update all the neighbors of uh, the switched vertex in the low degree part, and so this actually takes no more than square root of m time. So the main idea, the main challenge is then to maintain the edge counts, and in our paper we show that we can maintain the edge counts between these 4 blue pieces efficiently if we actually do the above steps. So when a low degree vertex switches, we recompute all its data structures. We can afford to do so because uh, the number of its neighbors are only square root of m. On the other hand, we might lose some information if we're only updating low degree neighbors of a high degree vertex. So I wouldn't have time to actually go into the proofs, but in the paper you can find them. You can generalize the combining idea to get a better, in some sense, a sublinear in n worst case update time randomized algorithm, which works on an oblivious adversary. So basically, in our algorithm, in this algorithm, we start with a random partitioning of the vertex set V into k sets, to which the adversary is oblivious to, and we would again just maintain half respecting cuts on all of these k vertex disjoint subgraphs, and for any update we would just now use the delta update time algorithm on each of those k vertex disjoint induced subgraphs. However, the number of edge counts that we now need to maintain are k squared. And the combining step is essentially going to take k squared time. But what we note is that the probability that an update is of the form that each of the endpoints of the updated edge are in the single vertex induced subgraph is at most 1 over k. So this actually allows us to sort of balance the update time between the costly updates and the less costly updates. So again, we use the delta update time algorithm, and if the two vertices involved in the update are actually in the same set, let's call that so if both of them are in the same set VP, then we're spending some amount of time, which involves updating all the neighbors, which takes delta update time. We need to pay the combining cost, which is k squared, and to actually use the delta update time algorithm, since each of those subgraphs contain only n over k vertices at most. So this is the cost from the delta update time algorithm. And the case when we have vertices in different subgraphs, in that case, you only need to pay the combining cost, which is order k squared. And sort of optimizing for k gives us k equals n to the 1/3. And putting everything together, this would give us an update time of n to the 2/3. And we can sort of use the probability amplification result of Bernstein to get the same update time with an additional polylogarithmic factor with high probability. So the point here to note is that the expected update time is actually due to the oblivious adversary, and if we want to make this if we want to make a high probability guarantee, then we can use the result of Bernstein as a black box, and we can convert this to an algorithm which takes tilde O n to the 2/3 update, worst case update, with high probability. So now I'd just like to conclude this talk with open problems and directions. So we would like, in fact, to have more efficient MPC algorithms, which only take sublinear in machines and memory per machines, such that with constant number of rounds, constant number of active machines that we're using per round, and fewer number of messages. So this first open problem is sort of based on the direction of the dynamic MPC algorithms that have been recently studied by Italiano et al. And note that based on our current work, we know that we can actually get an algorithm with roughly the same parameters as mentioned in this point number 1, but without a constant number of active machines per round. So the active machines are the machines which are involved in the communication. So this seems to be a major challenge, and it would be interesting to get an algorithm with this complexity. But the second natural open problem is just to improve the update time beyond square root of m in the deterministic setting. We note that although our algorithm is a square root of m amortized update algorithm, we can get the same update time in the worst case by periodically rebuilding the data structure, which is a standard technique in dynamic algorithms. The third open problem would be to get algorithms with small adjustment complexities. So except the delta update time algorithm and the distributed algorithm, our other sublinear update time algorithms actually have high adjustment complexity in the worst case. So it'd be interesting to get faster randomized and deterministic dynamic algorithms with small adjustment complexity. In the static setting, well, the major open problem is to compute, let's say, half respecting cut in small O of delta rounds in the congest model. The best known algorithm takes roughly delta rounds in the congest model. So thank you again for coming to my talk. Please feel free to reach out to me if you have any other questions, and if you have any other insights, or if you would like to talk about this problem. Thanks.